Okay, I think we're good. So we are back on track here. So everybody take a look. Assuming this comes up. There we go. Okay, so in order to get this one right, you've got to catch something. So this is about chemistry and biology students. So I'm going to put a C for chemistry right here and a B for biology right here. It says 300 students take chemistry, and it says they've got to take chemistry or biology. They can't take both. So if we put 300 here, that means we've got to put 100 over here, right?
Yep. Yes.
None of them are in the intersection. There's also none on the outside, and there are 400 altogether. So I'm going to put an n equals 400 here. So that's going to be our sample spaces, all 400 of those students. So the probability of biology is 1/4. It's the 100 out of 400. The probability of C union B, so that's going to be chemistry union. That's an or. Biology, that's going to be 100%. That's going to be a 1. We're going to do a 1.0. And then the probability of the intersection, since that's an and, nobody's going to be taking chemistry and biology, so that's going to be 0. That's going to be impossible. D.
Would it be all right if we just wrote them percent?
Yeah, that's fine. Okay. Okay. Does anybody know what we call it when the intersection is empty? When this set over here can't have anything to do with this set over here? Okay. Those are called mutually exclusive events.
Oh yeah, after that.
Yeah.
Yeah.
Okay. So mutually exclusive events. That's when we have the empty set or the null set. We can call it that. Okay, so what we're going to do today is there are times where we have events where one event impacts another. We get a lot of information when that happens. So we're going to do something called conditional probabilities. And conditional probabilities are written like this. That little bar right there makes it so it reads this way. We're going to say, what is the probability of A? So what's the probability of the first one in this little notation, given the fact that B has already occurred? So here's the formula for it. So this is the conditional probability of A given B. So this is the probability of A given B. It's the probability of the intersection of the two of those things divided by the probability of B happening. So we're going to follow this formula, and we're going to see if we can figure out why it works. So here's example number 1. So it says 100 people were surveyed about their food, their favorite food. Let A be apples and B be bananas. So they like apples and like bananas. Okay. If one of them is randomly chosen, find the probability of A given B. So in other words, find the probability they like apples given the fact that they already like bananas. So we're going to follow the formula. So the probability is probability of A intersect B on the top and probability of B on the bottom. So probability they like bananas. Remember on this it says n equals 100 here. So probability they like bananas is 40 out of 100. Oh, take that back. 39 out of 100. 39 like bananas. Probability they like bananas and apples. So that's going to be 9 out of 100. So this is a complex fraction. I'm going to flip this one over and we're going to multiply. So I get a 100 on the top, a 39 on the bottom. So I get 9 out of 39, both of which are divisible by 3. So this is going to end up being 3 over 13. Okay, everybody okay with that? Okay, I'm going to keep this right here, okay, because that 9 over 39 is going to come in handy. Take a look at the next one. The next one is the probability they like bananas given the fact that they already like apples. So if we set this up using the formula, it's this. The probability of B intersect A, we're going to switch the order there, divided by the probability of A. This one's pretty easy. The probability they like apples, 60 out of 100. Probability they like bananas and apples, that's going to be the 9 out of 100. So again, I'm going to take that and I'm going to flip it over. 100 on the top, 60 on the bottom. So I have 9 out of 60, which I can reduce to 3 out of 20, and this would be the answer. But again, I'm going to keep that around. Does anybody see a way you could figure that out? Just figure out what I'm looking for is a 9 over 39 and a 9 over 60 just by looking at the diagram. Okay, hang on one second. Got a couple people. So the question here is, why does the formula work? Here's the answer. If B has already occurred, or if the second one on the list has already occurred, it effectively reduces the size of the something space. I'm hoping that's a pretty easy one to fill in. What's the word? We'll do it in a minute then. Okay? Luke, you wanted to tell us how we can figure it out?
So what you have is you have the intersection divided by the probability of bananas or divided by the probability of apples. So that'd be 9 divided by 39 or 9 divided by 60.
Okay, so here's the deal on the first one. So I'm going to highlight this in green. So for this one right here, B has already occurred. So what's happened is we know that we've already chosen someone who likes bananas. We know that we're in this circle right here. So how many people in that circle? 39 people in that circle. We know there are 39 people that like bananas. How many of those 39 like apples? 9. So it's 9 out of 39. Okay, we can reduce that, of course. For this one right here, this would be probability of bananas given apples. So if they like apples, we've already picked somebody who likes apples, then we want to know what's the probability that they like bananas also. So that would be 9 out of the 60. So what it effectively does, instead of having a sample space with 100 people in it, it has a sample space with only, in this one, 39 people in it, or this one, 60 people in it. So what it effectively does is it reduces the size of the sample space. So on this one, we used the formula to figure out what the answer was, and then we kind of verified it by looking at it. We're going to do the opposite on this one. We're going to figure out, hey, let's just figure out what the answer is, and then let's just confirm that the formula actually works. So a cupcake is chosen at random from a bakery. Find the following conditional probabilities. So probability of vanilla, given that it's got blue frosting. Probability of vanilla, given that it's got blue frosting. Can somebody tell us what the answer is? Zach? 5/12. It is 5/12. He's right about that, because we have effectively limited this sample space to just those 12 people, okay, or cupcakes that got blue, or got blue, and we want the ones that are vanilla. So the answer on this one is going to be 5/12. That's the answer. Let's double check and make sure that the formula works. The formula would be this: probability of vanilla intersect blue divided by the probability of blue.
Yes, it works.
What's the probability of blue?
12.
12 out of 21, right? What's the probability of vanilla intersect blue? 5 out of 21.
Yeah, cancel out.
Flip that one over, 21 on the top, 12 on the bottom. The 21s would cancel. We end up with 5/12. Everybody good with that? Okay.
I like it.
Probability of white given chocolate. Probability of white given chocolate.
6/13.
What do you think?
6/13.
6/13. How'd you get that?
Because I did basically what we did on the last one, but I just flipped it around so that it's only the answers of the chocolate.
It's only the answers
and
for the
then
chocolate.
wherever the white is also.
Yep, because if we're
top.
given the fact that it's chocolate, we've reduced the sample space to those 13 chocolate cupcakes, and we want to know the probability of white. So it's going to be the white ones out of the 13 that are chocolate. There we go. Okay, don't say anything. Look at the next one. All the vanilla cupcakes have been sold. That's a lot of information. Probability of choosing blue frosting. So all the vanilla ones are gone. There's a condition. Zach?
It would be 7 over 13.
It would be 7 out of 13. In fact, it's the same line we're talking about here. It's just the probability of blue given chocolate rather than white given chocolate. So it's going to be 7 out of 13. Okay, any questions? Okay, next one. It says Miss Doty collected data on students and what type of devices they have. And it says find the following. Probability Samsung. We need something from this first, though. Yeah.
How many there are?
How many there are altogether, okay? Can somebody describe that?
Neither.
Gab.
They don't have neither.
They don't have either, okay? So they don't have a device, okay? So this is no device. So we need to know what N is. We need to know how many people there are in her class or how many people she surveyed. So that would be, if we add them up, 35?
25.
Okay, 35 in the sample space.
Projected also.
Probability Samsung,
25 out of 35.
25 out of 35, so that would be
5 over
5 out of 7 if we reduce that. Probability Samsung, given that they have a device.
Wait, this is actual data?
No.
Wait.
No. Okay, because
Yeah,
how would you, what would we put the 6 as? Are we counting that as just like another phone brand, or are we counting as we don't have it? Because that was changing.
that means they don't have a device.
Then it becomes like
Okay.
20, yeah, 25 over 29.
What is it?
It's gonna be like 25 over 29.
Okay, so they have a device, so that limits the sample space. It's not out of 35, it's out of the people who have a device. So it's this guy right here, and it's the ones that have Samsung and have a device. So there are 25 that have Samsung and 29 that have a device. So there's our answer on that one. So again, it's effectively reducing the size of the sample space. Okay, don't say anything out loud. Would you find the probability of Samsung given that they have an Apple? Raise your hand if you've written it down on your paper.
I'm stuck between two.
Okay, I'll give you another 20 seconds. Get something written down. Okay. Hopefully you've got something written down. If you get stuck on something, let's rely on the formula. So the formula said this. We would do the probability of Samsung intersect Apple divided by the probability of Apple, right? So, probability of Apple. 14 out of 35. Probability of Samsung and Apple, the intersection, out of
Yes.
35. So that's going to be 10 out of 35. So if I flip this over, I'm going to have 10 out of 14, which is going to be 5 over 7. Would you raise your hand if you got 5 over 7? Oh, very nice. Good job. Okay, any questions so far? Okay, flip the page over. So this is nice because what we can use is, because these are kind of related to each other, these probabilities are related to each other, we can use this formula to figure out whether or not we've got independent or dependent events. So A and B are independent if and only if, so this goes both directions. That's what an if and only if does. If the probability of A given B is exactly the same as the probability of A. So what this is saying is B doesn't matter at all. Or the other way to say this would be the probability of B given A is exactly the same as the probability of B. So going backwards or forwards, if either one of those things is true, then they're not dependent on each other. Yeah, Mason.
So basically, if you and them and there's nothing there,
If the condition of B happening already doesn't influencing the probability of A happening, yeah, then they're independent, okay? So we're going to come down here and we're going to check and see. So I'm going to leave the formula at the top here. So this is the cupcake data again. It says the probability of choosing blue frosting, is it independent from choosing vanilla cake? So we're going to determine this two different ways. These 3 rows right here, would you calculate the probability of blue given it's vanilla? Okay, so these 3 rows right here. And these 2 rows, would you calculate the probability of vanilla given that it's blue? Okay, check and see if that's the same as the probability of vanilla. Okay, go ahead and check those. I'm going to freeze this. we're going to do the first one.
Yes.
Okay. Are these equal?
No.
They're not equal. Okay. So the answer on this is no, but let's make sure, whoops, let me change colors. Let's make sure we understand why they end up the way they do. So this one is the probability of blue given vanilla. So that means it's going to be vanilla. So that shrinks the sample space. It's not 21 anymore. It's only 8. And 5 of them are blue, so that's going to be 5/8. Any questions about that one?
No.
Okay. If we just say the probability of blue, we haven't shrunk the sample space at all. We take all the blue ones. That's going to be 12 out of the 21. 12 out of 21 does not equal 5/8, so the answer there is no. So let me take a look at the other one. Make sure we get that one right. This is going to shrink the sample space into just the blue ones. So that's these guys right here. Probability of vanilla given that it's blue, 5 out of the 12. So that's why that's 5/12. Okay, we shrunk the sample space there, but then we want to say, hey, what's the probability of vanilla? Vanilla is 8 out of 21, and because those aren't equal to each other, we should have gotten a no either direction. Any questions?
No.
Okay. Let's take a look at these couple of problems here to finish this off. Are having an Apple device and having a Samsung device independent of each other? You can check it either way. So the probability of an Apple given a Samsung would have to be equal to Apple, okay? So you can check that one. Or the other one you can check is the probability of Samsung given Apple has got to be the same as the probability of Samsung. So let's check this really quickly. We'll do the Apple versus Samsung one, okay? Probability of Apple given Samsung. Probability of Apple, given that it's Samsung, that was 10/25, right? And the probability of Apple? 14 out of, how many were there altogether?
35.
Ooh, altogether, just that flat probability of Apple, it would be 35. Okay? So if we reduce the 10/25, we get 2/5. And if we reduce 14 35ths, so 7 goes in here twice, 7 goes in here 5 times, so we get 2/5. So the answer on this one would be yes, oddly enough. Doesn't happen very often that those are independent like that. And just for the heck of it, if we want to check and see Samsung given Apple, so Samsung given Apple would be 10 out of the 14 in that sample space altogether. So 10 out of 14, and the question here is, does that equal probability of Samsung period? So remember, there are 35 in this class altogether, so that's going to be the 25 that like Samsung, or have Samsung over 35. So we end up with, let's see, 2 goes in here, 5/7. And 5 goes in here, 5 and 7. So the answer to that is yes also. All right, great. Let's move on. So this last one, example number 6, this one kind of makes sure that you understand how that formula works, because there aren't numbers here. These are just probabilities. So would you read the problem and would you put those probabilities in place? Okay, a lot of times it works well if we find the intersection first. So start building from the inside out. So this would be French and Spanish. What percent take French and Spanish?
30%.
30%. Okay, so I'm going to put a 0.30 here. 20% take only Spanish. So I can put a 0.20 here. How do I figure that one out?
Well, 90 minus.
Luke?
So you take the total people inside the Venn diagram.
Yep.
And you subtract what you already have.
And how many people are, when you say inside the Venn diagram, you mean inside the circles?
Yeah.
Okay, so how many are inside the circle? What percent? Yep, 90. So 90 minus 50, this is going to be 0.40, 40%. Okay, we're missing something here. Yeah.
We need 10% on the outside.
We need 10% on the outside that aren't taking anything. Okay? So, probability of French given Spanish. D, what do you think?
3/7.
How'd you get 3/7?
Well, you have to take what's intersecting in between.
Uh-huh.
That's showing the French speakers who also are taking Spanish. Then you gotta take the total of all the French students, because we're asking out of all the French students, how many of them are also taking Spanish?
It's not 3.
Okay, this is the probability of French given that they're taking Spanish. So the Spanish is going to shrink the sample space from 100% down to just Spanish is 50%. So this is going to be 0.50 here. D. Okay, now we need the intersection. How many of them are taking French given that they're taking Spanish? Or what percent?
3/5 essentially.
Okay, 30%, so this ends up being 3/5. Okay, or if you wanted to, 0.60. Everybody good there? Okay, opposite one. Probability that they're taking Spanish given that they're taking French. D,
It's 3/7.
how'd you get it?
Because you're taking the total of all the Spanish students who are taking French too, so that's the intersection, which is 3, and then you gotta take the total of the French.
Okay, what percentage are taking French? How much have we shrunk the sample space? It used to be 100%, what is it now?
70%.
Okay, so 70%, so 0.70, and we want the ones that are taking Spanish, so what is it?
30%.
Yeah, 30%, so this is gonna be 3/7.
About 3/7.
Not a very convenient one, what is it? 47-ish percent?
42.
40,
43.
43%, so approximately 43%. Okay? All right, next one. Probability French given they're not taking Spanish. Careful with this one. Probability they're taking French given that they're not taking Spanish. We just shrunk the sample space. It's not 100% anymore. Keely?
Wouldn't you just take out anyone that's taking Spanish at all, so you just get 40%?
What's that?
Wouldn't you just take out anyone that's doing Spanish at all, so you just get 40%?
You're kind of in the right track, okay? But it's just, this is going to have something to do with it, but we're not quite there. Dane?
So wouldn't you just, because the only people that aren't taking Spanish are the 40% and the 10%, and the 40% are taking French, so it'd just be like 4 out of 5.
Okay, so I'm going to cross these guys out here. Anybody taking Spanish, this is, all these out here, they're not taking Spanish, correct? So we've gone from a sample space including 100% down to 50%. So the denominator is going to be that 0.50. Now, Keely, of those, what percent do we include for the numerator that are taking Spanish? Or sorry, French.
0.47.
That's going to be 0.40. So this is going to be 4/5, which is going to be 0.80. Okay. Any questions? Luke.
Do you still want our answers in fractions, or do you want them as percentages?
Same crew.
And our Roman.
I love piano. Piano was my favorite ride. I've only been on it like 6 times, but it was fun. I'm not going to that area.
So I'm not gonna do the
One
same
time
thing.
I went on it 4
To
times.
actually be able to like say like.
One time when I got season pass, I went 4 times in a day on Cannibal.
You know, she wanted to captain the
What even is that? 68 or 68? Like that
How
one.
much interval, like, you sat on it?
They don't say
I look, okay, I look up at the.
It's like you instead of an Auburn, you're
Oh,
an
yeah.
Auburn.
Oh, yeah, yeah.
I got bigger. I know, it's so fun. The G-forces are crazy. It's like, man, it looks like you're gonna hit the
You go low.
Oh, and then it does the like corkscrew upside down. I was like, you almost fall out at that part.
Oh.
Like literally, you can feel your legs slipping.
Well, you can have it.
You know the new guy? Yeah, I went.
That's easy. I don't want to.
Is that the conditional equation?
I had the.
Is that right?